Hello everyone, this is Mashmi. Today I'm here with another interesting problem which was sent to us. So this is based on mechanical properties of fluids. So let's look at the problem. A rod of length 6 meters has a mass of 12 kg. It is hinged at one end at a distance of 3 meters below the water surface. So, what weight must be attached to the other end of the rod so that 5 meters of the rod is submerged? Find the magnitude and direction of the force exerted by the hinge on the rod. The SG, that is the specific gravity of the material of the rod, is 0.5. So, let's first visualize the diagram. So, we have a rod of length 6 meters. It has got a mass of 12 kg and it's in the water surface, hinged at one end at a distance of 3 meters. So suppose this is the tank containing the water surface, and let's mark the level of water here. This is the level of water, and we have a rod which is hinged such that the region which is under the surface of water, that has got a height of 3 meters. So let us take this rod as PQ. Now we need to attach some mass to the other end, that is, they are talking of the end Q. Attach some mass here. So this is the weight in fact. Attach some mass here, and we need to find out this mass such that 5 meters of the rod is submerged. So let's take this point as R, and because of this weight, PR, that is the portion of the rod which is within the water surface, PR is equal to 5 meters. So this is as per given in the question. We also need to find out the magnitude and direction of the force which is exerted by the hinge on the rod. So what force is exerted by the hinge at this point on the rod? Again, that force should be thought of in terms of its components. As you can see that there is an angle of inclination here which calls for that. The SG of the material of the rod has been given. Now let's have a quick look at the diagram. We have the rod as PQ, and let us suppose that the center of gravity of the rod is represented as the point G. So this gives us that PG should be equal to GQ, since G is the center of gravity of the rod PQ. So PG should be equal to GQ, and as the net length of the rod is 6 meters, so this gives us each of this as equal to 3 meters. Now again, looking at the submerged portion of the rod, we know that 5 meters of the rod has been dipped under the water surface. So that calls for another center of gravity for the submerged portion. So suppose G dash is the center of gravity of the submerged portion. PR of the rod. So this tells us that we'll have G dash somewhere here, and we may write that PG dash is equal to G dash R, and that's equal to half of 5 meters, which is 2.5 meters. So these are the things that we have in hand. W is the weight of the rod. So let's assume the weight of the entire rod, that will be at the center of gravity, that's WC, weight of the rod. W is the weight of the rod. PQ. Now, density of the rod is also given. The SG of the material of the rod, from there we know the density, it's 0.5. So, talking of CGS units, the density will also be 0.5 gram per centimeter cube. But if we consider the CGS, the SI units, so density of the rod will be equal to 0.5, this is in gram per centimeter cube, and multiplied with 1000 we get the density in SI units. So this is 500 kg per meter cube. Once we have the density, and we can easily find out the volume now. So we suppose that for the submerged portion, V is the volume. V is the volume of submerged portion of the rod. So now, as we have the volume as V and the density of the rod is also known, let's have a look into the mass of the submerged portion. So, mass of the submerged part, that's nothing but equal to the density times the volume. We have the density. Let's look at the density times the volume. So the volume here, now look at this. We have, how do we find that? Just have a look at the length. We know that for the length 6 meters, the mass is 12 kg. So what will be the mass of the portion of the rod of length 5 meters? So in that case, the mass will be 12 times 5 by 6. So that's equal to 10 kg. So this is the mass of the submerged portion of the rod. Now we have the mass of the submerged portion, we have the density of the rod, and we also have the volume of the submerged portion. So it's easy now to calculate the volume. Volume will be equal to the mass divided by the density. So 10 divided by the density, which is 500. So that's 0.02 in SI units. Now we have the volume. Now let us look at the forces which are acting on the rod. So if you take a look at the forces, here one of the forces we have is, we have the force due to buoyancy, the upward force, which is trying to bring the rod back into position. So we have that, and we have the buoyant force and the weight of the liquid displaced. So the force of buoyancy, so this is buoyancy, force of buoyancy is equal to Fb, and this is nothing but weight of water displaced So let's look at this force of buoyancy. We can write this as Fb, and this is equal to, force is nothing but equal to the, we can use this formula here, mass times the acceleration due to gravity here. So V rho g. Now what's the volume? We know that, we have calculated it right now. It's 0.02 meter cube. We have rho coming up, rho, this is water, so we have 1000 in SI units, and G is 9.8. So this amounts to a value of 196 Newton. Now once we have the force of buoyancy, let's now look at the equilibrium of the rod. So the weight should be hung in such a way that the rod is maintained in equilibrium. So for equilibrium of the rod, the upward and the downward forces should balance each other. Now what are the downward forces acting here? We have the weight acting in the downward direction and we have the weight hanging here. And the upward force is only the force due to buoyancy. But then there is an angle of inclination here which needs to be taken into note. So if we look at the diagram again, we have these angles coming up as theta, and this is the angle alpha that we have made with the rod, and this angle is theta. So you can imagine the forces to get resolved into the two parts. We have the components of the reaction force that's equal to r sine theta. We'll have this. Let us assume the reaction force to be r. Then we have this coming up as r sine theta, and the vertical component, this is given as r cos theta. It's because of this component that, or this is the component of the reaction force which is exerted by the hinge on the rod. This component is trying to make it up, move it upwards, but then there is this weight to balance it. So this component is actually the force they have talked about here, the force exerted by the hinge on the rod. So they are talking of this r cos theta here. And let's look at the force of the components of the upward and the downward forces which are inclined at an angle alpha. So in this case for FB we have two components again, and this is nothing but trying to rotate the rod, and the rotating force is nothing but torque. So we need to take the sum of the torques, and since the rod is to be kept in equilibrium, the sum of all torques should equate to 0, and torque is nothing but the force acting multiplied by the arm of the couple. So the arm of the couple, if you take note, for the different forces it's different. When we consider FB, the arm we have to take is P and this is G dash, PG dash. When we consider the weight W, we need to consider the arm as PG, and when we are concerned with the force mg, then the arm of the couple will be PQ, and of course we need to consider the components of the couple here. So the component here will be nothing but the sine components. As you can see the angle here that is made, so the components will be nothing but the sine components. So let's have a look at the components here. For FB, it is the force multiplied by the arm of the couple. As I told you, the arm in this case will be PG dash and sine alpha. This is only in the upward direction, which is trying to make the rod move upward. So if we take this upward force as positive, then we'll consider the other two forces W and mg as negative, being in opposite directions. Or you can just carry on with the reverse thing. You may consider these two as positive and take FB as negative, which doesn't change the result in any way. So let's look at the component W. We have W coming up here, and we have the arm of the couple as PG and sine alpha, and for the last we have mg and then the arm of the couple as PQ, and we have sine alpha again coming here, and this is equal to 0. So ultimately if we work this out, we get mg, and this is sine alpha gets cancelled out on all sides. We have PQ here, and we have FB PG dash minus W, and this is PG. Let's put in the values. We have FB as 196 Newton, PG dash, that's equal to 2.5 minus W, which is the mass of the rod multiplied by the acceleration due to gravity, 9.8, and we have PG coming up, that's 3. So ultimately we get from here mg PQ as equal to 137.2. I advise you to go through the calculations. Sorry for any mistakes. So this is 137.2 by 9.8 times PQ, which is 6 meters, the length of the entire rod. So this gives us a mass of around 2.33 kg. So hope you get this. What weight must be attached to the other end so that 5 meters of the rod is submerged? So we are to add a mass of 2.33 kg at the end Q such that 5 meters of the rod gets submerged inside the water surface. So this is the first part. Now for the second part, we need to look at r cos theta component. So this will cause the rod to have translational equilibrium. So for translational equilibrium of the rod, let's look at the components here. We have in the upward direction the components as r cos theta and FB, and in the downward direction we have W and mg coming up. So let's equate the two to get the equilibrium condition. We have r cos theta plus FB, which is equal to W plus mg. So working on this, we need to find out r cos theta. That's W plus mg minus FB. So W, mass of the rod, times the acceleration due to gravity, plus we have m coming up as 2.33 times g, that's 9.8, minus FB, which is 196, all in SI units. So if we work this out, we get the vertical component as minus 55.6 Newton. So since this component is trying to move the rod upwards, so that's why the negative sign comes in that regard. So this is just indicating the direction of the force. The negative sign just indicates that the direction of the force is upward, that is opposite to the direction in which the rod is getting submerged because of the mass m. So hope you enjoyed the problem. Do keep posting more problems and we shall take effort in solving them. Thank you.